Hello everyone, my name is Vineet Singh. I am a software engineer and I'm a part of the VTune team at Intel. And for those of you who have already attended the previous talk, you are already familiar with Yuri and Asaf. They'll be helping me with the Q&A session. Before we get started, I want you to I would like to remind you that you can post your questions. There is a questions icon on your screen, and I'll get to your questions towards the end of the talk. So let's get started. Yuri, we are on time, right? Okay.
Yes, we're good.
Okay. So Intel has offered this new memory technology, Optane persistent memory, which is persistent. It's like DRAM, provides extra capacity to you. All those things sound amazing. But as an end user, the main question in your mind is, how can I benefit from this new memory technology? And that's what I'll try to cover in this talk. Uh, First thing we'll do is I'll go over what are the things that you need to know about this new memory technology. Need to be aware of what are the good things about it and what are the trade-offs about using this new memory technology. Just like any other hardware, this is not a golden bullet. There are particular use cases and scenarios where this technology will help you. And in order to know if you can benefit from this technology, you need to know about your own application. So the second thing I'm going to cover is what you need to know about your own hardware that you are running on and the software that you are running. And then persistent memory can be PMEM can be used in couple of modes. One is memory mode and the second is app direct mode. And they both have their strong points. They both have their use cases where you need to use them in order to get the max out of it. So what I'm going to do is I have divided the most common use cases into these two categories. And I'll give you an example of some of the use cases that you can detect before you actually have the hardware. Obviously, you want to know if this particular technology will help you even before buying it. So the idea here is that you will collect performance data on your DRAM only system and then try to find out if Optane persistent memory can be useful to you, can benefit you in solving your own problem. So we'll go over first some of the use cases for memory mode and then some of the use cases for app direct mode. And just a reminder, keep posting your questions after we are done with these topics. I'll address the questions at the end of the talk. Intel Optane persistent memory. So Intel Optane persistent memory is memory. The product comes in DIMM form. So basically it's like a DRAM stick. It sits on the same slot as your DRAM memory module, the DRAM DIMMs, where you put the DRAM DIMMs. The same slots are used for PMEM DIMMs as well. And you can put up to 6 persistent memory modules per socket. I think there is a typo here. Sorry about that. You can put up to 6 memory modules per socket. And as I mentioned earlier, this new technology can be used in memory mode and app direct mode. And I'm gonna go into details of what memory mode is, what app direct mode is. First thing I would like you to know is what are the benefits of using PMEM? What are the new things that it provide that can be useful to you? So most important thing is this is cheaper than DRAM. So per GB cost of PMEM DIMMs is lower than per GB cost of DDR. It provides you with higher capacity. So these DIMMs come in sizes, capacities 128 GB, 256 GB, and 512 GB. The usual DRAM that you use on your system, 32 GB, 64 GB, this is way larger compared to that. It can be used as a persistent memory or it can be used as a volatile memory. So you need not persist your data structure all the time. There is a way to use this technology just as volatile memory as in case of DRAM. It's way faster than your SSD. The latencies are order of magnitude lower than your SSD. So you get a large capacity main memory, which is the performance is equivalent, kind of similar to DRAM. That was the good part. Now, in order to use this technology, there are few things that you need to be aware of. The first thing and the first and foremost thing is that the performance of PMEM varies with the traffic pattern that it's observing. Whatever software you are running, whatever the memory access traffic pattern is being generated, that will affect the performance you are getting out of PMEM. So the things that you need to consider here are sequential versus random traffic. Sequential traffic gives you better performance compared to random traffic. Reads versus write. Writes are costly compared to read to PMEM. So read intensive workloads are a good fit for PMEM. Performance is lower than DDR. So the latencies, the usual latencies that you will see will be around twice the what you see on DDR. And DDR, your DDR DIMMs and your persistent memory DIMMs, they sit on the same bus. So there are two slots per channel in Cascade Lake, and the DDR DIMMs go in one of the slot and the persistent memory DIMMs go in another slot. So they are sharing the same bus. These are the things you need to be aware of. We'll go into details of how these things can affect different use cases. So let's move on to what you need to know about your application. As I said, this is not a golden bullet, and you need to know if it's useful to use persistent memory in your particular use case. And in order to find out if persistent memory is a solution for you, you need to understand what you are running on your system and your hardware. Some of the things that you need to know about your workload and the hardware that you are running on, I have tried to jot them down, a superset of them. You don't need all of these metrics information in order to determine a particular use case, but uh, this is the superset of all the information you need to determine if any of the use cases are applicable to your scenario. So first thing, let's start with the application. If you are going to use persistence part of the persistent mode of use of PMEM, you need to understand what are the data structures and allocations. And this is true even in volatile use case in a particular scenario. I'll get to that. You need to understand the file IO patterns if your IO is your bottleneck, and that's what you are trying to solve with persistent memory. A very important metric for persistent memory is the working set size or the active memory or hot data size. These are different names for the same thing. Out of the total memory allocation that your application is doing, what is the frequently accessed part of the data? So how much, for example, if you allocated 300 GB on your system and your application is going to use only 100 GB of data very frequently, that becomes your working set size or active memory size. This was with respect to application. With respect to system configuration, for different use cases, you might need the information about what kind of CPU you are using, what kind of memory you are using, what's the size of memory, and what's the type of DIMMs that you are using on the system, what's the type of storage device you are using in the system. Basically, these things are resources, and you need to know the max of these resources. What is the ratings on these different devices? Same goes for network device. In particular use cases, you need to understand that network can become a bottleneck after you switch to persistent memory. So you need to be aware of what kind of network device you're using. And for each of these components, you need to understand what is the utilization from your application. So we talked about memory. You need to understand what's the size of the memory, what's the type of the memory available on your system. You also need to understand what's the utilization by your application. So memory utilization, memory bandwidth, read write ratio, these are the common things that you need to understand about your application. Same goes for CPU. Utilization, kernel mode utilization, IO weight. These are some of the things that will help you determine where is the bottleneck on your system and how can PMEM help you solve that bottleneck. One of the crucial metric that really helps in determining if your application can benefit from PMEM is Intel top-down microarchitectural analysis metric, TMA metric. These metrics are available through perf or through our tools for Intel architectures, and these help you determine the uh, memory, the resource requirement from your application. So they come in really handy. As I mentioned before, you need to understand how your application is using the software and network devices available on your system. So IOPS, throughput, and queue depth are the common metric that you need to understand about your storage requirements. And network throughput is something you need to be aware of. Again, this is the superset of all the matrix, all the information that you need from your system on a DRAM only. Need to understand about your application on a DRAM only system. And once you have these informations, you can, for particular use cases, a subset of these information is utilized to find out if PMEM can help you solve a particular problem. So these are a lot of metric, and if you attended previous two talks, there are a number of tools available out there in order to collect these metrics. What we are offering in VTune team is a bunch of analysis type that have a really nice coverage with respect to the metric that I mentioned. The tool that will come in really handy for finding out PMEM suitability for your application is VTune Platform Profiler. So with VTune Platform Profiler, what we have tried to do is give you an entire picture of the system. What are the components on the system? What are the resources available? Plus, how is your application using those resources? So you need to understand what is the CPU, memory, storage, and network, and all those information is available on your using Platform Profiler. We also provide PMEM specific metric once you have the PMEM hardware, and in that case, it really helps you monitor performance and tune performance when you have the hardware. There are other types of analysis like hotspot analysis, microarchitecture explosion, and memory analysis that give you more information about how your application is using the hardware, and they give you application specific information. So let's move on to the memory mode. This is the first mode that you can use PMEM your hardware in. I would like to start by giving an overview of what the memory mode looks like. This is your standard memory hierarchy for DRAM case. Your DRAM is your main memory, and you have CPU caches. Now, PMEM becomes the main memory in case of memory mode, also known as 2LM mode, because two-level memory, that's what 2LM stands for. Your new main memory, PMEM, is actually slower than your previous main memory. So the performance will take a hit here. What happens here is that your DRAM becomes a cache. It's a near memory cache, and the performance difference between your main memory is mitigated by using the DRAM as a cache. So caching, if your application is able to cache frequently access data in the near memory cache, you will see performance comparable to your DRAM hierarchy that you were seeing before. And the most important thing here is, for using memory mode, you don't need to change your code. Take your code from a DRAM only system and run it on a memory mode system. It will run in the same way. The performance difference will depend on your application characteristics. So let's move on to the use cases. Where can memory mode be useful to you? What I'm going to do is I'll give you different scenarios where memory mode can be useful to you. I'll give you an overview of the scenario. What is the value of using PMEM in that particular scenario? What are the required metrics? And how can you go step by step based on the data that you have collected from a DRAM only system in order to find out if this particular use case is applicable to you? So let's start with a simple one: memory capacity bound application on a single node. In this scenario, what's happening is your application requires a lot of memory capacity, and on your system, whatever the memory capacity you have available is not able to meet that criteria. So what happens is your application will start swapping, and that swapping can hit your performance. So here, what we are trying to find out is basically, are you memory capacity bound, and is that behavior actually hitting your performance? So the first step of finding out if you are memory capacity bound and if your performance is taking a hit is, are you using the available memory fully? So that is captured in memory utilization. And if memory utilization is close to 100%, let's move on to the next step. First thing you need to check is memory utilization should be nearing 100%. Then second thing, you should have major page faults. So if in case you are starting to swap, you will start seeing major page fault. Disk activity will start happening because you are swapping and using the disk. So you need to correlate wherever there is disk activity or high CPU utilization in kernel mode to high memory utilization. If that's happening, you are swapping to the disk. And the next step that you need to find out is, are you taking a performance hit because of this swapping behavior? So check if the execution windows where you are swapping do those correspond to low CPU utilization? If do, then it means your CPU utilization is taking a hit because of the swapping behavior. And another sanity check is, you just make sure that your DRAM bandwidth is not saturated. So when you run all these steps on data which you have collected by running your application on a DRAM only system, and you satisfy all those criteria, you know you are memory capacity bound. You can use PMEM to provide additional capacity on your system, and that will stop this swapping behavior, and you will see a better performance on your single node. This is an example. I'm going to quickly walk through it. In this scenario, what we are seeing is your memory utilization, which is covered by the first graph, is hitting 100%. In the same execution windows where memory utilization is high, you see disk activity. And corresponding to that, if you look at CPU utilization is dropping to a very low value in the same regions. So all those things combined together tell you that there is swapping happening because you don't have enough capacity on your system, and memory bandwidth is not saturated in those execution window. All these graphs are from Platform Profiler, and once you run the, if you are able to collect platform profiler data and run these steps, you will know if your application is memory capacity bound. The second scenario that I'm gonna walk through is DRAM displacement. So what's happening here is your application requires a lot of memory capacity, but it's not sensitive to DRAM bandwidth and latency. So basically you can let go of some of those costly DRAM on your system and replace it with PMEM, which will provide you the capacity in a cheaper way. So the idea here is to decrease the cost of a single node. What you need to do here is once you run your workload on DRAM only system, the first thing you need to look at is your top-down memory analysis memory bound percent. If your memory bound percent is less than 30%, that definitely means your workload on that particular system is not bottlenecked by memory bandwidth and latency. If you are between 30 to 45%, that's still a case that you want to explore further. If you are above 45%, that definitely means your application running on the system is very sensitive to memory bandwidth and latency. Now, once you have found that, the second thing you need to check is the read-write ratio. As I said before, PMEM is highly sensitive to read-write ratio of the application. Reads are cheaper compared to write. So you need to find out if the read-write ratio is less than 40%, then you are definitely good to go. If it's between 40 to 60%, you still want to run the workload on a PMEM hardware in order to find out if the performance is comparable to DRAM. If you are heavily write intensive, above 60%, then PMEM you will see a performance drop if you run it directly. Now, there is a particular scenario where this even if you are very memory bound and write intensive, PMEM can work for you. The scenario is if your workload hot data completely fits into the near memory cache. Now all your accesses are coming from the near memory. You don't have to go to PMEM every time. That means you will see performance comparable to DRAM. So if these checks fail for you, what you need to do is check for working set size. And if that working set size, the size of hot data fits in your near memory cache, the size of DRAM that you plan for your memory mode system, you will still be good to go for PMEM and the performance will be comparable to DRAM only system. Let's look at an example. Again, these graphs are from Platform Profiler. Platform Profiler gives you the TMA metric in a nice single graph where different type of bottlenecks are stacked on one on top of each other. So as you can see, this particular application is 20%, around 20% memory bound, which satisfies our criteria of less than 30%. And when we look at the read-write ratio, you can see that this is a read intensive workload. So this is a nice workload where you can replace some of your DRAM with PMEM and see comparable performance on the memory mode system. The third scenario is a node consolidation scenario, and this is requires a bit more analysis, but the rewards are better. You are able to reduce the number of nodes that are required for running your workload. So the idea here is that you have a workload which is running in a distributed system, and the amount of the chunk of work that you assign to a single node is limited by the size of available memory. So for example, you have a 384 GB node, a bunch of 384 GB node, and you require 10 nodes because your application requires that much memory. And the idea here is that if the memory capacity is the only bottleneck for the amount of work that you assign to a single node, then you can increase the capacity and assign more work to a single node, and that will in turn reduce your total number of nodes required for the workload. So here, what you have to do is you have a bunch of nodes running the workload, pick up a subset of those nodes and collect data, basically sample out some of the nodes and collect data from them on the DRAM only nodes. and you will need extensive information about what is the system configuration and how each component on the system is being used. The first thing that you have to check here is available memory per node is limiting the amount of work that you are assigning to the node. So basically you are using more than 50% of available memory on the system. That's your first check. The second check is just like in the previous case, you need to find out if your workload is bandwidth and latency sensitive or not. PMEM, in case of PMEM, you need to have a workload which is not heavily sensitive to bandwidth and latency, since it has lower bandwidth and higher latency compared to DRAM. So that's the second check you need to do. The third check you need to do is basically third, fourth, fifth. Those checks are about when you start assigning a bigger chunk of work to a single node, you want to be sure that other components of the system, the CPU, the storage, and network, they don't become your new bottlenecks. So you should have enough headroom in your CPU in order for it to handle more work. Same goes for storage and network. How you can do that is basically CPU utilization, storage throughput, and network throughput, storage IOPS compared to what the devices are available on the system. And in case of CPU, you might be running an older version of CPU. For example, you are running a Broadwell system. Need not worry about that, because you need on the new system, you will have better CPU, for example, a Cascade Lake CPU. So you need to keep that in mind as well when you are talking about the aggregate CPU requirement. Last but not the least, you are assigning more work to a single node. So there is an expected performance hit that you need to you might take. You need to be aware of your SLA requirement. So if 5% performance hit is okay with you, or 10% performance, less than 5% performance hit is okay with you, all those things you need to be aware of that. Once you have this data, you have run through these steps, you can find out how much more work you can fit on a single node. And that's definitely a good thing in any case. Now, this was all about memory mode, where you don't need to modify your application and you can just go ahead and run it on a memory mode system. In app direct mode, you need to modify your application. So what we are going to do is quickly go over what app direct mode means, what's the memory hierarchy, and then we'll talk about a bunch of use cases here as well. So what we are doing here is your DRAM and PMEM, they are sitting side by side here. So PMEM is just another resource which your software needs to manage. And it can be volatile or persistent. With DRAM, you can consider that as the fast region of main memory, and PMEM you can consider less fast region of main memory. And this does require code changes in order for you to determine where you want to put your data structure. DRAM, where you want to allocate memory, in DRAM or PMEM. The first case here is displacing DRAM. It's similar in use case to one of the memory mode use cases, but the implementation is different. So what you need to do here is find out if you have two categories of data structures. One of them is more frequently accessed, one of them is less frequently accessed. What you can do is put the more frequently accessed data structure on your DRAM and put the less frequently accessed data structure on your PMEM. And the idea here is that your cost of single node will go down. So you run your workload on a DRAM only system. The steps you need to do is check out memory utilization should be more than 50%, because if it's less than 50%, you can just replace the DRAM with a smaller size, for example, 32 GB DIMMs to 16 GB DIMMs. Once you have found out that there are two categories of data structures that you can put on your main memory, your hot data structures should fit on the DRAM. Oh, my bad. It's DRAM. Okay. Now, the second scenario that we are talking about is the IO bottleneck. Here, what you are talking about is you need some persistent data, which is available on your storage media. But if you place that persistent data on your PMEM, you will see a performance boost. Here, the steps that you want to go through in order to find out if if the first thing you want to find out is you are actually IO bound. That particular IO traffic is actually hitting your performance. So CPU utilization should be low. IO weight is taking. There is a significant IO weight because of this traffic going to the storage media. And the second thing is, in a lot of scenarios, the data on storage media is huge. You can't move the whole thing to PMEM. Actually, you can with this bigger capacity, but the particular scenario that we are talking about, what you can do is find out if there is a subset of data that you can place on a faster media. So, for example, you have some metadata or logs that are very frequently accessed. You can move that to PMEM and you will see a performance boost here. So that was a couple of examples of use cases for app direct mode. This is not an exhaustive list. I want to stress that heavily. There are many other use cases where persistent memory can help you benefit. Some of the use cases are, for example, time sharing application. You have two categories of application that you are running on the same system. One of them requires less amount of memory. That means they nicely fit into near memory cache, and others are not that sensitive to bandwidth and latency. So you can time share on the same system and your cost of ownership will go down. There are new application. People are coming up with new application which can use this large amount of memory, and they don't have to worry about distributing their application across different nodes, because now the whole requirement can be satisfied by a single node. IO caching is another use case. You put PMEM media in front of your storage media as a cache, and that gives you better performance. It mitigates your IO bottleneck. Uh, Yesterday in PMDK, there was PMDK presentations. PMDK contains bunch of new persistent data structures that user can exploit, and using PMEM get the persistency benefits. So depending on your particular use case, you can, depending on your particular scenario, you can come up with a novel use case for persistent memory. If you want to know more about how people are using persistent memory in real world, I have provided some of the resources here. You can go to Intel Optane persistent memory page. There you will find bunch of examples of how people are using. DAOS is a storage, is an engine which makes your storage faster. There are HPC application people have experimented with using PMEM. VMware has released a white paper using memory mode. There are papers on in-memory graph analytics where people have been doing graph analytics in memory because now they have a huge amount of memory available to them. So it's a new technology. You need to understand the basics of it, and then you can come up with n number of use cases for this new technology. Some of the resources regarding our tools that can help you determining your application suitability for PMEM are available at the persistent memory tools link that I have provided here, and VTune. You can find VTune at software.intel.com/VTune, and VTune has bunch of features that can help you both determine the suitability of your workload for persistent memory, as well as once you have the hardware, it will help you understand your performance and tune it for persistent memory. So that was all from my side. Let's see what questions we have from the audience. Asaf?
Yeah. So thank you, Vineet. So first, there was interest in many specific questions for the PMEM technology and the difference between memory mode and UpDirect mode. We answered most of those questions, and I think you covered the details. I just want to point out that the PMDK sessions are tomorrow,
Oh, my
and
bad.
so you still have a chance, right, to register, go to those sessions, and learn more about PMDK and how to work with UpDirect. Another set of questions here that I'd like you to relate is that people are interested in. I mean, we shown some uh, examples of how you can use VTune to get
Mhm.
the information that you talk about here. But can you talk more specifically about which metrics are available in VTune for this methodology, and what specific features do you recommend people to use in order to do this type of analysis?
Okay. So if you go back to the slides that I had in the slide that I had in the beginning, which talked about what is the superset of all the metric that you need in order to do such a suitability kind of analysis. Uh, Most of the system level information is covered by VTune platform profiler. As you can see, I gave you examples about different graphs, memory bandwidth, latency, storage, network, CPU, all those metrics are covered by platform profiler. Shri talked about this in the previous talk in more details. If you need application specific information, like what are the memory objects and what's the size of those allocations, you need to go to memory analysis and microarchitectural exploration. That gives you more detailed information about how your application is using the hardware. So about information about what objects are there and how you can move it around in app direct mode, all those information is available in VTune profiler, microarchitectural exploration, and memory analysis. In order to and these tools together give you very high level of coverage with respect to all the metrics that I have used in my analysis and I have mentioned. Hope that answers your question. Asaf, you have another one?
Yeah. So thank you for clarifying that. And can you also relate specifically to the top-down TMA metrics
Okay.
that we have in VTune, and what specific support is there for persistent memory?
So uh, if you go for VTune platform profiler, you will get let me go to the example that I showed you. So if you go to VTune platform profiler, that will give you a high level idea of TMA metric for in these 5 categories. What's the percentage of pipeline slots that are retiring, what are the front end bound, what's the percentage of front end bound, core bound, bad speculation, and memory bound pipeline slots for you. And I know that's a term I'm using, but if you need to go into more details in order to find out how these pipeline slots are defined in top-down microarchitecture analysis. If you go to VTune microarchitecture analysis, there you can get further breakdown of these 5 categories, and you will have a metric which talks about what are the pipeline slots, what are the cycles that are installed at PMEM. So on a PMEM system, app direct or memory mode system, it gives you more information, further breakdown of these categories, and helps you tune your performance for PMEM.
Thank you. Another question for you. In memory mode, where
Yep.
DRAM basically works as cache and
Yep.
PMEM is the main addressable memory, right?
Mhm.
Um, what options do we have in our tools to monitor the DRAM cache efficiency?
So that's a very good question. We have bunch of PMEM specific metric in all the analysis type. So for example, if you run platform profiler, while running your workload on a memory mode system, you'll see metric like near memory cache miss rate. So you will be able to get exactly what percentage of traffic is missing your near memory cache and going to PMEM. In addition to that, it will also give you information about what is the bandwidth you are getting from PMEM, what's the latency for your PMEM accesses. And there is a special feature in Platform Profiler which also gives you per DIM information about PMEM. So for example, you have 6 DIMs on your system and you are running your workload. When you run a platform profiler collection, it will give you information about how each of those DIMs are doing, what's the bandwidth that you are getting from each of the DIMs, what's the access pattern that each of the DIMs are seeing. So we have a nice set of features both in platform profiler and the other part of VTune like microarchitecture analysis and hotspot analysis, which are very specific to PMEM memory mode and give you the information, the kind of information that you're looking for. For example, the near memory cache miss rate.
Okay, thank you for the answer. Yeah, at this point, I think we addressed most of the questions that were coming in.
Okay. Okay, thank you everybody for attending, and we have a workshop coming up that will give you more information about how you can tune your performance. I see that a lot of questions were about tuning your performance for PMEM, and the next workshop talks about it. So do attend that. Thank you.